it's going to be, first we're going to do this one. From 0 to 2 pi, you have your z is constant, r is constant, and then d phi times r hat. So you have zr integral from 0 to 2 pi d phi. What is r hat? Here is r hat. It's cosine phi I hat sine phi j hat. So we do this. Cosine phi I hat plus sine phi j hat. We have CR. That's the integral. What's the integral of cosine? Sine. So you get, I'll put the I hat in front and then sine of phi evaluated between 0 and 2 pi, right? And then what's the integral of sine? Okay, so I'll have a minus j hat and then cosine of phi from 0 to 2 pi. Let's evaluate this. What's the sine of 2 pi? 0. What's the sine of 0? 0. So this term becomes 0. How about this one? What's the cosine of 2 pi? 1. And then what's the cosine of 0? 1. So you have 1 minus 1, which is 0. So this whole thing becomes 0. So that's the 0. So this one is out. We have this one. So let's flip it out. I have r squared. R squared dt k hat integral from 0 to 2 pi. R is constant, k hat vector is constant. So what's the integral now? Yeah. It's going to be r 2 pi times r squared times k hat. So now b, therefore magnetic field B is going to be all this stuff, which is u naught I over 4 pi and 1 over r squared plus z squared to the 3/2 power. And what's left from the two brackets there? Inside. This. 2 pi r squared k hat. And 2 pi here cancels with this, you get a 2. So B is going to be u naught I r squared over 2 times r squared plus c squared to the 3/2 power. Okay. So that's the magnetic field for a current field. It was a little bit of work, but that's the result. So that's a distance c above the loop, right? Distance c above the loop. Give you a minute, and then I want to ask one more question, and then go from there. So, what if, what's the magnetic field at the center of the loop? Not quite. Yeah, at the center of the loop. Magnetic field at the center of the loop. What do you do?
The maximum?
It would be the maximum. And what do you do to find this? You let z equal to how much?
Yes, 0.
Yeah, so you're not above the loop, you're at the center. So if z is equal to 0, it's going to be a simple, yeah. let's see. So at the center, C is equal to 0. Okay? At the center of the loop, C is equal to 0. Let's substitute 0 for Z. Okay? 0 for Z, you get 0. What is R squared to the 3 halves? Just R cubed?
R cubed.
Yeah, R cubed. You have R squared on top over R cubed, you get 1 over R. So it becomes this. U naught I over
2R.
just 2R. That's the magnitude. U naught I 2R. Yeah. That's the, how much it is. That's at the center of the loop. Now, if you want to create a strong magnetic field, you would use a coil, meaning you take a loop on top of a loop on top of a loop. You make many loops. So here's a coil. It's kind of heavy. It has 3,400 loops.
34.
So 3,400. Obviously, when you wrap them, the radius would change, right? It starts to get larger. But we'll just ignore the radius change. We just say it's about the same. And then, so if I have a distance there, if there is current here, there will be a magnetic field towards you. How much is it? That's the equation. But I need to multiply by the number of loops. Because I don't just have one loop producing that magnetic field. I have 30-something hundred of them, right? So if you have 2 loops on top of each other, they'll produce twice the magnetic field. Assuming the current runs the same way, right? We don't run them opposite, but they're running this way. Yeah. There are coils in there, but to accelerate things, you need a potential difference. Yeah. Magnetic fields, they do not do work. Yeah. Electric fields, they're the ones who accelerate things. Yeah.
Can we launch something through there?
Huh?
Can we launch something through there? Or do we know?
There are things that you could, yeah. But if you have a magnet, and if there is a current here, they might repel each other and so on, yeah. No, yeah, I mean, yeah, maybe. If mg is, and the magnetic force are equal to each other. Yes?
Are these the same principles behind MRIs? Or
That one, yeah, you would have in that case, we'll discuss solenoids. So for us, we'll just discuss the magnetic field part of it, but the details are,
no?
yeah. X? Which F? You need a charge to feel that force.
Okay, so let's say that like the charge was on the z-axis, where would it go?
And it's moving, maybe? So it will feel a force at a certain instant. Yeah. Depends on what direction it's moving. If it's moving to the right, then it will be towards you, towards us. It's a cross product, QV cross V. Yeah.
Wait, for at the center of the loop,
Yeah.
K hat also, right?
Just magnitude here.
Just
Yeah. So if I have a coil, so let's say you have n loops, not 2, not 3, maybe 2 or 3 or 7. Then the magnetic field for a coil, of course, is going to be n. Right? Okay.
Professor,
I'm going to discuss Ampere's law now. Yeah.
if the coil is in N loop and it's a long coil, isn't it mean like they have the different
Different
magnetism?
distances.
Yeah.
Yeah, you can do that also. Yeah. I'm assuming here this distance is short compared to this distance.
Oh, so you like neglect.
Yeah.
Okay.
So, we're going to discuss Ampere's law next, and it's one of the equations that we will have, one of Maxwell's equations, at least partly. So, let me erase this, just tell you what Ampere's law is all about, and then go on. You see the use of our law? You have to do cross products and integrate and all that stuff. But if there is symmetry, you can take advantage of it, and that's where Ampere's law is useful. They're equivalent to each other, but it's just a matter of usefulness. Just like, remember Coulomb's law and Gauss's law. So let's erase here. Let me pause this. So we start Ampere's law by itself.